we are going to go to the first presentation from 2019 Nobel Laureate in Physics. So you see, we have Nobel Laureates in Physics, Chemistry, and Medicine. So all are together. And also SIPS, we have a very strong three medically related symposia: oxidative stress, new technologies in medicine, and COVID. But here, not blah, blah, blah. It is a scientific analysis, scientific development on the field. So unfortunately, sustainability today, basically sustainability was developed as a political concept, and it became so confusing. And politicians say, we follow environmental sustainability. It doesn't make any sense, environmental sustainability. Environmental is part of sustainability. So that's why we have SIPS, or so many fields of science together. Now, the Nobel Laureate in Physics, Professor Queloz from University of Cambridge, or now he is in ETH in Switzerland, ETH-Z in Switzerland. He will speak about, the title is a little bit, it is Exoplanet Revolution, but actually it is more down to earth. Is the blocks of life. And life is the same in Earth, is my interpretation, not his. Hopefully he agrees with that. Where he is? Oh, here is there. Okay. It's the same. Blocks of life are the same on Earth and in a different planet. So basically, there is a bottom line which is that goes together. So this is what we will hear in the next presentation. So although it is exoplanet, it doesn't mean it is not sustainable, because this helps us develop new things for the Earth also. Please, Professor.
Thank you. Well, we're going to dive into what's called blue sky science here, but actually the point that would be relevant for this series of talks is the impact that this has on a kind of new understanding where we're sitting, and you will see that also the way this topic is being addressed, it's kind of telling us something about possibly the future of science, how science will evolve in the future, addressing big challenges. Okay, exoplanet revolutions. Why revolutions? I mean, it's fair to say that in the last 30 years, we have moved for one world where we were the only planetary system orbiting our sun, the star, to almost an infinite number of planets sitting, orbiting stars around us in the universe. What does it mean? How much can we learn from this? I'm going to give you a little bit of a 101 introduction into this. Well, first, this is something we know quite well. These are the planets of the solar system. These are the planets for a long time that will be best understood, because we can fly there, we can send probes, and we'll keep doing that in the future. But more profoundly, we have studied this system quite a lot, and without going into the detail on the planetary formation and what we understand of that, I would just open what we understand is a planet, and there is something which is very, very, the key of the understanding how you make a planet is the structure of the planet that is based on something in the middle that we call the core, which actually acts as a seed when you are making the planet. Essentially, when you have a planet like the Earth, you only have the seed of the planet and end up with a rocky planet. When you have a bigger planet like Jupiter or Saturn, you also have a seed, which is very similar to the one you have established for the Earth, but the seed was so quick and so efficient that it managed to trap a lot of gas, which is making the planet very big. As a physicist, when you see that, it's quite striking. How do you get so much diversity into something which is quite simple, which is building up a structure, orbiting a star? And actually, these questions have kept people busy for a long time, trying to build up let's call it a theory, or let's say a model of the formation of the planet that was pretty much successful. It's based on another concept, which is the concept of the disk, or protoplanetary disk. This is one of the kind of pictures that astronomers can produce these days. This is a very early stars, very young stars. For us, early stars is billion years, so the sun is 4.5 billion, so this is very young. And if you look at the star, with the right equipment, which in that case, it's a kind of a telescope that looks in the same wavelength that your microwave, it's very sensitive to anything which is a little bit warmer than the background, which is the dark of the universe, which is not completely 0 degree, but not very far. And you produce this kind of map, which is a thermal map, essentially, of a structure, which is a disk structure, of the time when you establish planet. Well, when you see in the structure, you see grooves, you see structure here, and the whole story there is telling you something is going on here. And what is going on is the planet buildup is happening. Well, combining the structure of the disk and the idea that you build up a planet from the inside out with a core was the core element to establish the global theory of the planetary formations. 30 years ago, everything was absolutely convinced that all the planetary systems should look about similar. We should have small planet like the Earth orbiting in the same regions that is now Venus and the Earth. And we should have big planets like Jupiter and Saturn orbiting farther away. The reason for that is because the time to process the core and to establish this condensation effect, or you grab all the material, is much faster when you're a little bit outside because you have much more material available. It's related to the fact that what are the water and CO and CO2 you have in a gas form, when you get a little bit farther out, it becomes cold and becomes snow, essentially. So you have way more material, solid material to make the planet. Well, and everything has changed 30 years ago when we demonstrated the first planet orbiting under the star was not exactly like that. We detected a planet like Jupiter that was expected. They are big, they are the easiest to detect, but the big surprise was the planet like Jupiter was not at the Jupiter orbit. It was orbiting the star much closer than Mercury right now in our solar system. The time for this planet to orbit the star was a bit more than 4 days, which means it's 20 times closer to the orbit of the Earth. It cannot happen. It's impossible. This is part of what I'll call the discovery space in science. Essentially, science has 2 categories of developments. One which you expect based on some understanding of things works, and the unexpected. Well, actually, there is more unexpected than expect. And most of the time, you find something you were not at all aware of. And the reason why you do that, because you build new equipment that is going to extend our capabilities to see through the complexity of the world we're living in. It's valid for the small world, the big world is exactly the same. And what we did at that time, we demonstrated the planet could exist on another star, but they could be very different. Well, actually, it was a challenging time for me and for us, because nobody believed us. It was so awkward. It didn't fit the theory. I mean, how come you are flying, a lot of probes onto a planet in the solar system, and you have a good understanding of how the planet are formed in our solar system? How come could it be so wrong? Well, that's an interesting thing for you to dilute and to digest. I think until you really see something, you cannot imagine it exists. It's because it's the reality of where we are and we're working here. And until we have realized that there were completely other kind of planet elsewhere, nobody could have guessed. And actually, things have escalated quite a lot. And after a couple of years, it becomes obvious that these planets were real. And then it became obvious it was even more complicated than that. And the situation as is today is this one. Every dot you have on this picture, which is simply helping you to understand what is the mass, what is the size, and what is the distance of the planet. You have here the radius in the Earth unit, the mass in the Earth unit, and you have the period of the orbit in days here. Well, how we do that? Well, we use the star. We use the star. If the planet happened to just have the right angle of the orbit, it makes a transit. Transit helps you to find the size of the planet, so we got the radius. And the mass, we use simply the Doppler effect, which When you look at the stars, when you have an orbiting planet, then it's changing a little bit the speed of the star. It makes the speed of the star moving around, wobbling around, and that's how we detected. This is a technique we've been using to detect the first planet. Well, it looks easy the way I describe it. Actually, it's a technological achievement to do that. This is why it took so long to establish this many planets. The interesting feature of this diagram is when you look at the planet of the solar system, you see Jupiter, you see the Earth, and Venus. Now, to be fair, when you have such a kind of result in science, the first thing you have to ask yourself is, what is the limitation of what we can see with the equipment that we're using? And it's applied to anything you're doing here. So to help you through, without going too much detail, I would just add what's called a boundary limitation. So anything on the left side of this diagram, this hatched line, we can see. Anything on the right side, we can't. Because it's too difficult, because it's too unlikely, because there is a lot of problem with the stellar activities. It's a very challenging area. So the first thing you realize is the Earth and the Venus, they are to the boundary today. So today, we can't detect a planet like the Earth and Venus. It does not mean we don't want, it just means it's difficult. Well, actually, we're working a lot. That's one of my main activities still these days, is to try to improve that. I'm not the only one, and we shall detect these planets in the next 10 to 20 years, because I think we understand how to do that. But this is the reality that we are. Now, leaving this aside, already looking on the left side, there is something which is striking, is all these planets that you have on the diagram, essentially they should not exist, because they are not similar to the planet of the solar system. So essentially, what we have been doing is a bit like being a gardener and studying flowers in your garden and having plenty of roses. But one day you go to Brazil and you see this diversity of all this you can see in the forest there. So it's just seeing the world in a more wider way and to understand how we fit in. So this is where we fit it in. So right now we know that there is a couple of planets very extreme that called the hot Jupiter. This one over there on the top here. So the first one was one of them. It's a Jupiter but a very short orbit. We have some kind of a Jupiter-ish planet that are fitting here in terms of mass. We don't have them in transit because they're very unlikely. The size is found by transit. But we have this amazing group of planets here that are not supposed to exist at all. You may have heard the term of super-Earth, mini-Neptunes. This is what it is. These are planets that are sitting between the Earth in terms of size and mass, but they're not in terms of distance. They're very, very close. Look at them. This is just one day. This is 10 days. They are essentially grilled by the star, if the star is like the sun. And there is even more surprise to come in this diagram, because the new dimension you can do is ask yourself, well, if I look at the star tonight, what is the likelihood I will have any of this planet orbiting the star? So it's a kind of a complicated analysis to do, because you have to run through the statistics, you have to find out the limitation of each of the surveys, and so on and so on. But people have been doing that in the last years, and they come up with this kind of agreement that this is the reality of the occurrence of the planet around stars. Few percent of this very extreme Jupiter that may have moved from the location where they are right now in terms of our own Jupiter. There is very extreme effect going on when you form a planet. One of them is migrating the planet, moving and removing everything on the way. We have this 10-20% of planet that looks like Jupiter, our own Jupiter. It's interesting. So maybe there are a small fraction of the system that is similar on a way, because we only look at the more massive planet outside. And then more than 50 to 80% of the planet are clearly within this regime that are completely different from the one we have. And I was shocked, because we had this amazing picture that the solar system is a standard, is a norm. And actually we're not. And actually we're not at all. We are on a corner. How far on the corner, I don't know. Is it 1%, 10%, 0.1%, 0.01%? We don't know. But we will find out. Now comes the interesting reflections about this meeting. So we are looking at the universe. So we are in one of these planets in the solar system, which is in the corner in this type of diagram here. Does it mean anything? Does it mean that to have life, we need to be in the corner of this diagram? Or could you still have life on some of this planet there? It's a very interesting question. It's not very easy to answer because you have such a diversity of structure here you have to deal with. And to give you a bit more what's behind this, you can combine these two diagrams and you can build up what's called a density diagram. Mass, size, you get the density of the planet. Well, this is this diagram here. So every point with a square you have give you the range of error you have. There's a bit more room for margin here because you do the cube of the size, so it just escalates on the error. But that's what you get here. So you get the mass, you get the size, and to help you to see that, I added 3 different kind of densities. One which is typical for called giant planet, like Jupiter or Saturn. This is this kind of line here. So we see that Jupiter and Saturn fits very well along it, which is what you expect. This is the nature of this planet. Most of the planets we have found, there seems to be above, sitting above in this diagram, because the density is a bit less. The reason why, because they're very hot, they're very close to the stars. The very detail, we're not very sure, but that's at least the reality what it is. So something you may want to also notice in this diagram is you cannot explain Neptune, neither Uranus, by the same law that you explained Jupiter and Saturn. Essentially because this is seen as to be a failed giant planet in the sense that this planet was too slow to grab all the gas. So they missed most of the hydrogen and helium you had at the beginning. So you only ended up with a more massive gas. That's why there is a bit more dense, and it doesn't replicate this structure. It's sitting here. Now, you can imagine playing with the model in all directions, and one of them we do is we look what's called a water planet. The reason why we use water, because it's very, very well understood molecules and very high pressure in all different conditions, thanks to our colleagues in Earth Sciences that did that for the Earth. So we can build a planet only with water. Well, don't imagine the water on this planet is exactly the same that you have on the sea just next door. I think the water, certainly on the outskirts of the planet, could look like a liquid water, but inside, with the pressure and everything, is completely different. It's called ice water there. But you would sit along this diagram here that gives you an idea of the diversity of the planet we may be facing with. And then you have the rocky planet that are this green line. This is the Earth model. You can move the mass up, you move the size up according to the model, keeping all the model in line, and we do have a couple of planets sitting in this regime. So we have a very, very complex diversity right now to face with. We have planets clearly in all the regime, in all range, and we're talking about a planet which is 3 to 5 times the mass of the Earth. It can be sitting anywhere here. It can be rocky, it can be kind of water-ish, or it can be even more Uranus-like-ish. So again, coming back to life is very complicated, but that's the reality of the world we're living in, and we are one of these planets sitting just here in that corner here. Now, what can we say from this? So I want to give you a little bit of a glimpse of what is happening right now. So the tool we're using, when you think about that, is quite fascinating. We don't see this planet. We don't see them like a picture. We would take a picture. But we use tricks to understand and to get the mass and the size of this planet. We can even do better. I can even tell you what is the nature of the atmosphere of this planet without really seeing them. How does it work? Well, this is a diversity we have to deal with right now. So this is all the planet that we have in the universe. So not only the big ones and the small ones, we have all this regime here, and we really would like to understand what we're talking about. Can we say something about the ocean planet? Can we say something about the rocky Earth? Can we say something about all this planet there? So the trick is the following. When you have this configuration, which is called the transit configuration, there is 2 specific moments that you can use if you know exactly when it's going to happen. One of them is when the planet goes in front. It's called a transit here. And one of them when the planet goes behind. When you think a little bit about that, when the planet goes behind, that's the only moment when you only see the star, right? So if you have any device and you just record anything you get at that time, it gives you what's called a 0 point, a reference point. And as soon as the planet gets out, there's a bit of the flux, a bit of the light that is either coming directly from the planet because of the thermal radiation of the planet, or just reflecting like the moon, reflecting the light of the sun. So you will have a little bit of a difference then. You will have a bit more light in your detector. We use this effect to directly measure the temperature of the planet, for example. So you don't really need to resolve the planet. We can use this trick that there's a moment we can use the differences. Even more fascinating is this moment here when the planet goes in front. It acts as a bit of an X-ray for us, because part of the flux, part of the light from the star is going to cross the atmosphere, and other is not going to do that. So how it works, I want to show you something for you if you're not familiar with that, that will help you to understand how powerful is this technique. Well, this is a picture of the ISS. When you're on the ISS, this is a pleasure you can see. You can take a picture of this very moment in the visible, in that case. You can do that with your cell phone. And you have the moment when the moon is just close to set or to rise here. I don't really know which version it is. So what I want you to pay attention is this very, very small, tiny bit of distance here. This is the reason why we are alive, 10 kilometers. We only be alive thanks to these 10 kilometers. It's very, very tiny. This is to connect the sustainability element here. This is what we're talking about here. Now, pay attention to this if I take the very same picture at the very same moment, but I use another color, another wavelength. That's all terminology. We're not in the visible anymore. We are in the infrared. This is something that has changed. You see there is more distance here. Well, infrared is a trick the military is using to see the surface of the planet. At that wavelength, you go across the clouds, and you see the surface of the planet. This difference between the visible and the infrared is the reason why we have the global warming, because the reflection doesn't correspond to the energy which is being absorbed. There's a difference between the two due to the water absorption and CO2 absorption in the atmosphere. So it's interesting because essentially when you look at the planet in the infrared, the planet looks smaller. Or you see the planet without the atmosphere, essentially. You see the bare rock of the planet. Well, let's do another experiment and try to use a very specific color, which we're all very familiar with, which is the color where is sitting the ozone band. It's 9 microns. Ozone band will give you this. Much bigger, right? It's obvious here. Because ozone is sitting 50 kilometers above the atmosphere. The reason why is because it's been formed there. Is the escaping oxygen from the atmosphere, the 10 kilometers regime that's interacting with the solar radiations and producing the ozone layer, which is what you are sensitive here. So my little story, I hope, convince you that depending on the color you're looking at the planet, you can find out exactly what is the atmosphere of the planet. Well, that's the trick we're using. So you may have heard that we have this fabulous James Webb Space Telescope right now in operations, and that's one of the results that James Webb produced quite recently. And this is the size of the planet here, and the size of the planet, amount of light blocked, which means the size of the planet against the size of the star. This is expressed in part per million, so it goes, in that case, of the order 1%, and then plus minus fraction. And you see it's changing according to the color, which is the wavelength here. Well, this is the data you get, but then you can do a full retrieval model of that, and you can find out what is the kind of molecules that will exactly be matching best this set of data. And you come up with this kind of blue line, and then you can say, okay, the blue line that I fit the best is the blue line I can make, in that case, with water. So this is how we astronomers can detect molecules on planets. So we can do that today, and we will keep doing that more and more in the future, so we can study the atmosphere of this planet. So what do we do with that? How far can we do with that? Well, this is to give you a little bit of an idea of the level of possibilities which is happening. So let's imagine you detect water and oxygen on a planet. What can we say? Well, a lot and nothing at the same time. Well, depending on the assumption you're making on the planet, you can end up with something that would be the Earth, essentially, but also something could be very different. Because depending on how you play with the star can be different at different stage, depending how you play with the nature of the planet, whether there is water or not water. And pay attention, this water story is not just a detail, it's absolutely a key element here. Think about our sister planet, Venus. Venus is one Earth mass, and one Earth radius. There is no difference. We are twin. If you look at the system from above, from other stars, you can even guess that it's more likely there is life on Venus than on Earth, because it's the right distance to produce life. We're a bit too far away. Well, what is saving us is the global warming, because we have enough atmosphere on the Earth and a lot of water actually in the atmosphere that produces global warming that makes the temperature that nice level on Earth. But Venus is the one. What happened on Venus? It's just death over there right now, or at least the way we understand it on the surface of Venus. Maybe not in the atmosphere, but certainly on the surface of Venus. Because there is no water on Venus. And because there is no water, so nothing, I think, the situation, no water right now make this completely, end product of the greenhouse effect. And that's what we're having right now on Venus. Does it mean that Venus never had water? Or does it mean that Venus lost water? We don't know. Something we better find out, because it may be just a glimpse what may happen to Earth at some point. So just to give you an idea of this water, it's just not a detail. So we can do that. We can study this on looking at plenty of other planets, orbiting other stars, and we can find out how they work, how the kind of global understanding of the atmosphere interact with the surface of the planet. And we can learn without seeing this planet really a lot, and trying to bring us into perspective. So similarly, what I'm telling you right now is 30 years ago, what we did, we demonstrated the solar system as a global system is different from our own system. So there's a difference between what we are and then the diversity of the other solar system around. What I'm telling you right now is tomorrow we'll be able to tell you how much Earth and Venus and Mars are different from the many other planets that we have orbiting other stars. Because of course there must be this kind of planet somewhere, but maybe they are different. Maybe there has water, there's no water. Maybe there's plenty of water, we don't know that. This topic is quite fascinating because we moved to ideas that you could debate 100 years, and it was already the idea of debating about life was very ancient, actually. You have a Greek text mentioning the possibility and the likelihood there is life everywhere and in the universe and so on. Until the point when we're not only debating it, we're bringing facts. And that's one of the very nature of science, is not debating it, is bringing evidence and fact. They can still debate it later on, but it's way more difficult to debate in all directions when you have some fact to accommodate with. So this is what we're doing. So all the facts are getting together these days into that kind of topic. Well, the first fact I would like to just make sure you're aware of it, I mean, the idea of origin of life on Earth has made tremendous progress in the last 10 years. So far, before, we had a vague kind of concept that maybe the origin could be at the bottom of the oceans without a real theory, anything like, into the point where I know people are producing real full-scale modeling of origin of life on Earth. Well, this is a kind of the most updated result right now that the community seems to getting an agreement on of what you need to bring life on a planet. Well, first you need water. That's pretty obvious, according to what I've said already. Now, you need something else that's produced by the volcanic activity. So SO2, SO3, this is the kind of minimum condition you need, and that's bringing naturally when you have volcanoes. Interesting enough, if you're a chemist here in the room, it's HCN. You don't really connect HCN to life, and if you have HCN, you die, essentially. Well, actually, HCN is a pretty cool molecule. First, it's extremely useful to build up the early reactions of the origin of life. There's a lot of possibilities with HCN, and there is plenty of HCN in comets. And as you know, at the origin of the planetary system, there's a lot of comets falling on Earth. Just look at the moon, and you have an idea how much impact and stuff has been falling on planet Earth. So HCN is falling a lot at that time, so there must be a lot of HCN falling on. The atmosphere is boring, chemically speaking, and that's a big change because we move from the idea, the early experiment from Yuri Milner, that used to assume a very highly reduced atmosphere, producing a lot of energy, that bring what you need to produce the beginning of life into a situation right now where the atmosphere is neutral. The reason why it's neutral, because when you form a planet, it's pretty clear that right now the atmosphere is full of CO2, and you don't get much out of that, and you don't hope for the atmosphere to make magic and to make chemistry of life. So what do you need? And that's the new idea, actually, is, well, you use just the sun next door, the UV radiation of the sun. So all this, now there is no whole literature starting on that, and the original paper are there, starting in 2015, have led to a very interesting level of discussions right now on that. If you want to get into a bit more detail, what is happening is actually you can work through the chemistry of this. And this is one of the last papers, 2019 on that. When you start from this very basic element you have on the planet, on the surface of the planet, into flow, river, pond, and then you build up all the chemistry, the early chemistry element of life. You don't build life yet, so nobody has made life in the lab as of today, but they will tomorrow. It's pretty sure, according to the amazing progress being made on these elements. So the 20 amino acids being produced, the lipids, I think the nucleotides are produced by this chemistry. So what has happened here? Essentially, in the last 10 years, everybody's aware of that. The chemistry, the tool people are using to analyze the component has multiplied by 1 million times, I think, the capabilities to study stuff. Think about the study of the human genomes. That was a big stuff, 10 years ago, right? It needs an army of people on more than 1 year. Well, I can send my old piece of anything of my nails, anything to somebody, and 10 minutes later they will just go through my DNA sequencing. So this is what is happening right now. Computer has changed the game as well. Now you can do chemistry into computers. It's growing, and we're talking about network chemistry here. It's not only one reaction, it's a zillion reactions going at the same time. And when you do that, and you try to do the full modeling of this, and this is what has happened in the last 5 years, you come up with an extremely high yield producing the component of life, because it has to be extremely high. Otherwise, it doesn't compete against something else. I used to say, the big competition for life is shampoo. So you don't want to end up as a shampoo, but you want to end up with a chemistry which is giving you life. So this is life as we know it. This is the only life we know, which is life on Earth. It's already interesting because it gives you a kind of a baseline to study. It doesn't mean life is exactly the same, but it's very likely that the basic components should be about the same. That's the kind of assumption we're making. But that's where we stop. We don't do more than that because we open to much more possibilities on the complexity of other life, especially in slightly other conditions. You can think about life in Venus. There has been a claim about that. You can think about life in satellite of the giant planet, Enceladus, Titan. I think they are clearly liquid. It's not water, but there is possibility maybe something going on. We know there is a very fascinating organic soup going on there, and we're going to go there and as well. So it's a very, very complex topic, but it's interesting to realize this is happening now, and people are producing that. Maybe 100 years, we will have reached exactly the same level than for the particle physics. 100 years ago, Rutherford was playing with atom in his basement, essentially. 100 years later, we have a complete understanding of the nature of the matter, essentially. We're producing thermonuclear weapons, we're producing machinery to analyze the body. We have an amazing understanding of this. We control the matter, essentially. We're almost about to replicate the sun into experimental machinery producing the energy. Well, I do claim that in 100 years, it's very likely that we have reached the same level for life. So we should be able to make life. I'm not only talking about playing with DNA here. I'm talking about making life maybe a different way, and that would be a fascinating moment if we reach it in terms of all civilizations, because we see the challenge we're facing already with the tools that we have developed that could self-destroy ourselves so easily. So last slide to understand exactly how this is going to play together, how we're going to learn about this without going, because all these stars are very far away, and essentially, when I say we may understand life as it is on Earth in 100 years, we're never going to go to another planet in the near future, because of the energy challenges, the time challenges, this is completely out of scope right now. I'm not talking about 100 years, I should talk about 1,000 years, the minimum, to do this kind of big jump. What's happening is if you study at the origin of the Earth, which is very rich, you come up with these patterns for my colleagues of Earth Sciences. When you start from an astrophysical component, you assemble the pieces together, you lose a lot of gas, you have a lot of infold, which is really great, because most of the CO2, the carbon, is sitting somewhere outside in the solar system, so they have to fall in to make enough carbon available for life, actually, on Earth, and we have plenty, actually. So this is really falling on Earth at the beginning. There is a whole process when the heavy elements are sinking down and the light element are staying and floating away, floating on the top, which is key because you start creating the iron core that start the magnetic field. Magnetic field is certainly a very key ingredient here for the origin of life. And you end up with this very interesting moment when the atmosphere is CO2 dominated. You start the volcanic activity, you produce SO2, you may have some water as well as falling in and as well as coming from the inside out into the planet, and then something happened that paved the way for life. It's called a prebiotic element. We don't really know, and there's this idea of a process I mentioned before, and then everything changed. And then the atmosphere, the planet is completely different. So the concept here I would like to just make sure you understand is a planet is a living organism in a way. You don't have a static object because there is a permanent interactions between the surface, the liquid oceans, and then the atmosphere of the planet that keeps evolving depending on the nature of the evolutions. And it's very complicated, and it's very challenging to understand that on Earth because of the plate tectonic has completely removed most of the traces. We have very few traces from this very early origin. We have the zircons and very few of them. But what is fascinating is we have a couple of elements we can look around. The moon, because the moon was formed at the 20 to 30 million years after the formation of the Earth. So it's kind of an imprint of that time. That's why we're very interested about the moon, because nothing really happened very much after that time. So it's a milestone of the nature of the part of the composition of the planet Earth at that moment. And Mars, because Mars was about the same until first billion years, possibly with water, and we have evidence of this. And then, because of the small nature of the planet, the planet lost most of its atmosphere and has no really plate tectonic. So Mars is fascinating. This is why there is so much focus on Mars and so much exploration on Mars. And in the next 10 years, we will leave something that would be an amazing step for humankind. Last time we brought back sample from another body was the moon 50 years ago. Nothing yet has happened. We brought some tiny piece from some comet, but very, very tiny bits. So we will, in the next 10 to 15 years, bring back significant amount of sample from Mars. I think it's really a big step forward. It has never happened, something like that. And I can predict, whatever you think, you will understand that there will be a lot of surprise. And here I would completely disagree with the statement, the science cannot expect what to find. I think there is a lot that is not to be expected in science. And quite often, when you expect something, you get surprised about the outcome, what you're going to get. So the Mars sample return will be a massive change in our perceptions, and will have an impact on the formations, the understanding of the formations of possibly the early stage, the prebiotic moment, because it may well have been that life started as well on Mars at the same time than on Earth, which is in the first billion years. And we may see some chemistry evidence for that. Don't expect to find any animal here, but at least some chemistry evidence for that. So what is fascinating with this diagram is every stage here, when you look at the atmosphere, there is a very specific imprint which is being produced. And this is what I describe here. 3 different stages. The stage before life, the archane Earth, then when you start having life, the Proterozoic Earth, and then now. Well, technically speaking, we can detect this on any stars with a planet that would be similar. And it's going to happen. There is no limitations. You don't need to fly there. And in 100 years, we will have hundreds of planets that will be kind of like the Earth, not exactly like the Earth, with a clear understanding how they fit here. And then there's a lot of very interesting elements, even at the stage when there is modern Earth. When you talk about people asking at what time exactly do you see something is happening on Earth, well, actually, there's a couple of moments that you can identify. One of them is the great oxygenations, which is the moment when a massive amount of oxygen is being produced on Earth that drastically changed the nature of the atmosphere. That happened about 2 billion years ago. So I keep saying, don't be worried about being visible from any alien civilizations. It's too late. It has been already since 2 billion years ago. So anyone looking at us, that would be an advanced civilizations,
on planet Earth would be seeing since 2 billion years, there's way too much oxygen to make a story just for the nature of the planet. Something must have happened. So we're very visible in terms of life in the global universe since 2 billion years. So the question is, we have not been really visited, or maybe we have been, but we cannot look, we cannot see it, obviously. But this is what is the reality. The second main element here is, I think at the time then us, our species, started to completely transform the Earth. And it's not only 50 years ago, where it's very massive, accelerating, have a dramatic effect right now. It started already about 5,000 years ago. We started to be addressing the food problems and producing field and crops, and it has completely changed the Earth at that time. The Earth was very different, and you could already see some traces at that time. So somebody looking at us would have plenty of time to identify the growth of civilizations and to see there is life on Earth in the last 2 billion years, and they don't need to wait right now. So don't be worried about sending signal right now on this, because I think it's already kind of done in some way already. But we will be able to study that. We will be able to tell you that whether maybe we are the only planet like that amongst the hundreds of Earth-like planets around us or not. I have no idea what's going to happen, but this is the reality of science. So there is a very interesting element into that for this meeting, is how can we do that? Now, I hope you understood that right now I've been talking about a topic which is far beyond my comfort zone. I am a physicist, I'm an astrophysicist. I'm not a chemist. I'm not a biochemist. I'm not a biologist. I'm not a earth scientist. And there's a lot of stuff here that I had no idea really what it was before I started talking to these people and trying to understand what they were telling to me. So I think this is very fascinating also as what I call an interdisciplinary challenge here. Complex problem like this one cannot be addressed with only a single discipline. So it has to be addressed in a kind of a global team. And that is quite an interesting challenge, because the way the system, the educational system is working, the way the university operating, the way the funding agency operating, doesn't really fit with this kind of concept. It's very difficult to work through the, already established system because of this. So the kind of trick we're using, and I say we, a couple of colleagues in Harvard, in Chicago, and in Cambridge, in ETH Zurich, have started to develop a specific program for that. I just mentioned 2 of them, but there is others. So if you want to Google it and have more detail, what I call innovative collaboration. So we try to make it work. This is one of the reasons why I was interested to come to this meeting. It's just to send this message to you. I think this innovative collaboration and complex problem is applicable for global warming as well. It's applicable for AI as well. It's applicable to post-human as well. And these are really big challenges that go much beyond the technicality of it. There's a lot of sociological elements and law elements and economics element which is related to that. So the key here, we're just only going to focus on one key topic, which it's a momentum problem, which is trying to understand really why life, essentially. Why you have life in the universe. I think you have matter. We have some understanding why the matter structure like that. What about life? Is life an absolute follow-up as soon as you have the matter? It has to come. If you have the right condition, the right element, it has to come. Or is it completely unlikely, and it's just once amongst billions and billions probability, and we don't really know yet. The idea of pushing this program, it must be quite easy to develop life, but it doesn't mean it's easy to grow life. You may have maybe life somewhere and it disappear. Maybe it happened on Venus. Maybe it happened on Mars as well. And that is really something that we are going to find out here. So I will leave you with this, hopefully kind of this interesting statement that this is happening right now, and this is something that we will do. Not me, but the future generation of scientists, because this is really a vast agenda to solve this. I will stop here, and thank you very much for your attention.
Thank you very much. It's just so we have CO2, very important. Today, CO2 is the enemy of the world and Earth. And then we saw without CO2 we cannot live. So it depends how you manage it. Also, two things. He mentioned that it's chemistry, it's physics, it's everything, and everything. This is SIPS. You know, we have everything under one roof for synergy because the world is like that. This is my conclusions from this. So the more you see in the universe, the more you understand from our Earth. So you see, you need volcanoes to have life. You need explosion to have life. So they are not bad phenomena. So all are necessary. That's my interpretation, you can correct me. But all are necessary to have life. The key point is how you manage it. Thank you very much. We really appreciate it. Very fascinating.